On Sicily's eastern coast, Mount Etna isn't just erupting anymore, it's moving. The entire southeastern flank, forests, villages, ancient lava fields, all of it is sliding toward the Ionian Sea. And what terrifies scientists isn't the movement itself, it's that the sliding is accelerating and no one can agree on why. Some measurements show the drift speeding up after eruptions, others suggest something far stranger, that the mountain is responding to forces we haven't even identified yet. This isn't a slow geological crawl that takes millennia. This is measurable, documented, and according to leaked sensor data from 2024, getting faster every year. While researchers publicly maintain calm, private emails between monitoring stations tell a different story. Phrases like unexplained acceleration events and data inconsistencies we can't resolve appear again and again. When a volcano the size of Etna starts sliding, the assumption has always been that it will stop on its own, that friction, that the bedrock will hold. But what if that assumption is wrong? What if Etna's flank has already passed the point of no return and we're just watching the countdown? Mount Etna rises more than 300 meters above the Mediterranean, a giant built by millions of years of eruptions. But its foundation, the very ground it sits on, is far weaker than anyone wants to admit. The African plate has been diving beneath the Eurasian plate for eons, melting rock, feeding magma upward, building Etna layer by layer. But that same collision fractured everything underneath. Unlike volcanoes anchored in solid granite, Etna sits partly on ancient marine sediments, soft, compressible layers that were never designed to hold the weight of a mountain. Imagine stacking hundreds of heavy books not on a table, but on a thick pillow. The weight doesn't just push down, it spreads, it deforms, it slides. That's Etna. Every eruption adds more weight, every lava flow tilts the balance just a little further, and beneath it all, those soft sediments are slowly giving way. But here's what keeps geologists awake at night. Recent seismic surveys, some still unpublished, suggest there may be water infiltrating deep fractures beneath the eastern flank. Water acts as a lubricant, reducing friction between rock layers. If that's true, and the evidence is mounting, then Etna isn't just heavy. It's sitting on a slippery slope that gets more unstable with every passing year. The first clue that Etna has a violent history of collapse is written into the landscape itself. On the volcano's eastern side lies the Valle del Bove, a massive horseshoe-shaped scar, 5 kilometers wide and 1 kilometer deep. For decades, scientists assumed it formed gradually, carved out by erosion and repeated eruptions. But newer research is challenging that story. High-resolution imaging of the valley's walls reveals layers that don't match gradual formation. Instead, they suggest rapid, catastrophic removal of rock. In other words, a flank collapse. And it wasn't small. Offshore on the floor of the Ionian Sea, researchers have mapped enormous debris fields. These aren't scattered rocks. They're organised, massive deposits stretching for kilometres, the unmistakable signature of ancient landslides. Some of these deposits are older than human civilization. Others are disturbingly recent in geological terms, possibly just a few thousand years old. But here's the mystery that no one has solved. The debris patterns don't match current models of how volcanic flanks fail. Some blocks are far larger than any simulation predicts. Others travelled farther across the seafloor than physics says they should. In 2023, a team from the University of Catania ran new sonar surveys and found something even more unsettling. There are additional debris lobes they hadn't mapped before, buried under sediment, suggesting Etna's eastern flank has collapsed not once or twice, but multiple times. And each time, the sea absorbed the evidence. What remains unanswered is whether these collapses happened slowly, in stages, or if some were sudden, catastrophic events that generated tsunamis. The data is incomplete, the debate is unresolved, and the possibility that Etna could fail the same way again sits at the centre of every risk assessment. For years, scientists suspected Etna's flank was moving, but they couldn't prove it. The mountain sits partly underwater, and measuring motion on the seafloor is notoriously difficult. Then, between 2016 and 2018, an international team deployed a network of underwater acoustic transponders along the submerged slope. These devices communicate with each other, measuring tiny shifts in distance with millimetre precision. In May 2017, the instruments recorded something no one expected. Over just 8 days, the seafloor moved 4 centimetres. That might not sound like much, but in geological terms it was a shock. 4 centimetres in 8 days is not the slow creep of tectonic drift. It's a lurch, and it happened without any eruption, without any earthquake strong enough to explain it. Just movement. When the data was first analysed, some researchers thought it was a sensor glitch. They reran the calculations, checked the instruments, cross-referenced with satellite data. Everything confirmed the same thing. The flank had slipped. But the truly alarming detail, one that still hasn't been fully explained, is that the movement wasn't smooth. It came in pulses. For 2 days, nothing. Then a sudden shift. Then stillness again. Then another pulse. This stop-start pattern suggests the flank is catching and releasing, like a sticky drawer that jerks open in stages. And no one knows what controls the timing. Some believe it's tied to magma intrusions, pressure building underground and then releasing. Others argue it's purely gravitational, the mountain inching toward collapse under its own weight. A third, more controversial theory suggests deep-seated, faults are slipping episodically, triggered by factors we haven't identified yet, perhaps even tidal forces or atmospheric pressure changes. The data is public, the interpretation is not, and the lack of consensus among experts is, in itself, a warning. Since that discovery, Etna has become one of the most heavily monitored volcanoes on Earth. GPS stations track surface motion in real time. Satellites scan for ground deformation down to the millimetre. Seismometers detect every tremor. Seafloor sensors measure the slightest shift along the submerged fault. On paper, it's a perfect early warning system, but in practice, there are gaps. In late 2023, 3 seafloor transponders went offline for 72 hours during a storm. When they came back online, the data showed a discrepancy, a small but unexplained offset in position. Engineers couldn't determine if it was a malfunction or if the flank had moved while the instruments were dark. That 3-day blind spot remains a source of heated debate. Then there's the problem of interpretation. After the 2021 eruptions, GPS data showed the southeastern flank moving faster, just as expected. But some stations recorded motion in directions that didn't fit any model. A few moved laterally, parallel to the coast, instead of seaward. Others seemed to tilt, suggesting subsurface deformation that no one predicted. Dr. Alessandro Bonforte, who leads part of the monitoring effort, has been vocal about these anomalies. In a 2024 conference presentation, he showed unpublished data revealing that the flank's motion is not uniform. Some sections are sliding faster than others, creating internal shear stress that could trigger sudden failures. His conclusion was blunt. We are not monitoring a stable system that occasionally moves. We are watching an unstable system that occasionally pauses. That distinction matters. If Etna's flank is fundamentally unstable, then the question isn't if it will collapse, but when and how much. And the monitoring network, for all its sophistication, can only tell us what's happening, not what's coming next. The scenario that haunts every risk assessment is the same. A massive section of Etna's flank detaches and falls into the sea, billions of tons of rock, moving fast, displacing enormous volumes of water. The result would be a tsunami, waves racing across the Ionian Sea, striking the coasts of Sicily, Calabria and possibly Greece within minutes. Computer models have tried to simulate this, but the results vary wildly depending on the assumptions. How much material fails? Does it go all at once or in stages? How steep is the underwater slope? Change any of these variables and the wave height predictions swing from manageable to catastrophic. In 2022, a joint Italian-German study ran hundreds of simulations and found something disturbing. Even a partial collapse, just 10% of the flank, could generate waves over 5 meters high along Sicily's eastern coast. Communities, like Giare, Riposto and Taormina, would have less than 10 minutes to evacuate. But here's the deeper fear. Some researchers believe the real danger isn't a single collapse, it's a cascade. If one section fails, the sudden loss of support could destabilize adjacent areas, triggering a chain reaction. The historical debris field suggests this has happened before, and if it happens again, the waves wouldn't come in one pulse. They'd come in a series, each one arriving as people try to recover from the last. There's also the question of timing. Collapses can be triggered by eruptions, by earthquakes, by heavy rainfall saturating the ground. But they can also happen spontaneously, driven purely by gravity. The unpublished data from 2024 shows increased microseismic activity along the base of the flank, tiny fractures propagating through the rock. Some interpret this as normal, others see it as the mountain preparing to let go. The truth is, no one has enough information to say for certain, and that uncertainty is itself a risk. Predicting eruptions is hard, predicting gravitational collapses is far harder. Volcanoes give warnings, gas emissions spike, magma moves, the ground swells. But a gravitational failure can behave differently. The mountain might accelerate gradually over months, giving time to prepare, or it might go suddenly, triggered by a single event. A deep earthquake, a magma intrusion, even a storm weakening the slope. Right now, the drift averages just a few centimetres per year. That's slow enough that no evacuation orders have been issued. But it's also continuous. And once a slope begins moving under its own weight, reversing that process is nearly impossible. Scientists describe Etna as dynamically stable, a carefully chosen phrase that means it's not collapsing right now, but it's not safe either. It's holding, for now. What makes this especially difficult is that the forces driving the movement operate on geological timescales. A collapse could be centuries away, or it could begin in a single human lifetime. In 2025, after a particularly energetic eruption sequence, sensors detected a brief acceleration in flank motion. It lasted only a few days before slowing again, but it was enough to prompt emergency meetings among monitoring teams. The acceleration wasn't predicted by any model, it simply happened. When asked to explain it, researchers offered competing theories. Some said magma had intruded into the flank, temporarily increasing pressure. Others argued it was purely gravitational, the eruption shaking loose some internal friction. A third group suggested it might have been related to rainfall, water infiltrating fractures and reducing resistance. All three explanations fit parts of the data. None fit all of it. And that lack of clarity is deeply unsettling, because it means the next acceleration might come without warning and without time to respond. Mount Etna has shaped Sicily for millennia. Its eruptions have built fertile soil, drawn people to its slopes, and created landscapes unlike anywhere else on Earth. But the same forces that built the mountain are now pulling it apart. The ongoing drift doesn't guarantee a dramatic collapse. The most likely future is a continuation of what we see today: slow movement, occasional bursts of activity, and eruptions that reshape the summit piece by piece. But geological systems don't operate on predictable schedules. Etna's flank will keep moving, its underground plumbing will keep shifting, and gravity will keep pulling the slope toward the sea. Scientists aren't warning of an imminent catastrophe. They're studying a natural process that has happened before and will eventually happen again. Understanding that process is essential, not to create fear, but to build preparedness. Because even a mountain as mighty as Etna is not permanent. It grows, it fractures, it slides. And someday, far in the future or closer than anyone expects, part of it may fall. Until then, researchers continue to watch, instrument by instrument, knowing that even the slowest movements can be the most important. The debate over what drives the sliding continues. The gaps in the monitoring network remain, and the mountain, indifferent to all of it, keeps inching toward the sea.